Welcome to section 3.8, where we are discussing exponential growth and decay. This is a topic that you should have encountered in algebra, but we're going to be looking at it through the lens of calculus and see how the calculus background helps us better understand these algebraic topics. So, to start off, in general, if a function y of t is the value of a quantity y at a time t, and rate of change of y with respect to t is proportional to its size, then we say dy dt equals k times y. So when we say that the rate of change of y with respect to t is proportional to its size, that means the faster the rate changes, the larger the size gets, and the slower the rate changes, the smaller the size gets. If you think about it in terms of like population growth, if you start off with just a couple of people, and then that grows more and more and more, and we just keep going and going and going. At first, that rate of growth is going to be a little bit slower, right, for this group than it is maybe for going from this group to this one. The amount of growth happening is getting larger and larger, right? And that's what exponential growth is. But as the size increases, okay? So again, the rate of change is growing with the size. And this is that directly proportional relationship. This is the rate of change. This is the size of the group. And this is the proportion that goes between the two of them. It's the scale of it, where k is a constant. If k is greater than 0, so we're dealing with a positive constant, this is the law of natural growth. And if k is less than 0 or a negative, this is the law of natural decay. So looking at exponential growth versus exponential decay is just a matter of a population growing in size or a population shrinking, but still in an exponential way. Now for this first theorem here, it says the solutions to the differential equation dy dt equals k times y are the exponential functions y of t equals y of 0 times e to the kt. So a differential equation is just an equation that has a derivative in it, like this one does. It's an equation, it has a derivative. So this differential equation has solutions that look like this. And if you kind of picture these using different letters, you might recognize this formula as the exponential growth or decay formula. Right? We don't always use these same exact letters for it, but it is the same process. So in other words, as long as this relationship is true, we can use this equation, which is something that you learned to do back in algebra. We just don't tell you exactly why we're able to do it that way necessarily. So let's take a look at an example. Use the fact that the world population was 2,560 million in 1950 and 3,040 million in 1960 to model the population of the world in the second half of the 20th century. Assume growth rate is proportional to population size. What is the relative growth rate k? Use this model to estimate the world population in 1993 and predict it in 2020. So, as you can see, I got a little bit set up here. So we are assuming this proportional relationship. Again, that's this section right here. That means that we can use this equation that we just talked about. So I have that set up for us right here. Now, in this specific example, the p of 0, that initial amount that we're working with, we're starting in 1950. And moving on from there. So that's going to be our starting point. So it's going to be 2560 times e to the kt. And our first job is to solve for k. So we need to use the only other information that we have in this problem, and that is in 1960, the population was 3,040 million. So that means population not of 1960, but in the years between 1950 and 1960. So 1960 would correspond to t equals 10 years. So the population after 10 years is going to be 2560 times e to the 10k, right? Because t is 10, equals 3,040. Okay, with the understanding that these numbers are in millions. So from there, we go ahead and divide that through. So that's e to the 10k equals 3040 over 2560. From there, we take the natural log of both sides so that we can get rid of this e. That leaves us with 10k equals ln of this number. And divide by 10. So we get k is ln of 3040 over 2560 all over 10. And this is great work for a calculator. We get approximately 0.017185 for k. So our relative growth rate, the k value, is going to be, so it's about 0.017, so that's going to be about 1.7%. So it's growing at a rate of about 1.7% per year. So our new formula, as opposed to this original version where we didn't know what k was, our new formula is going to be P of t equals 2560 e to the 0.17t. Okay. Oh, whoops. Actually, let me fix that. Let me just move this. So that's going to be 2560 e to the 0.017. I'll go ahead and put the whole number, 185t. Better to be too accurate than not accurate enough. So to answer the question, world population in 93 versus 2020. Remember, we're dealing in terms of years after 1950. So 1993, it's been 43 years. So this is P of 43. In 2020, it's been 70 years. So we get 2560 times e to the 0.017185 times 43. This one will be same thing, but evaluated at 70. So in 1993, we get approximately 5,360 million people. And in 2020, we're looking at approximately 8,524 million people. Now, of course, if we're talking in terms of thousands of millions, we're really just talking about billions. So, if we were just saying this, we would read this as in 2020, the population is expected to be 8.5 billion people, approximately. Okay, so all algebra work and algebra concepts that exist because we have this relationship, this directly proportional relationship with a derivative or a rate of change from calculus. Next up, we can look at, similarly, exponential decay, just like we looked at exponential growth. So the half-life of radium-226 is 1,590 years. A sample of radium-226 has a mass of 100 milligrams. Find a formula for the mass of the sample that remains after T years. So I'm going to go ahead and call this M of T, because we're talking about mass. So that's going to be M of 0 times e to the kt. And our initial mass, that M of 0, was 100 milligrams. So that's 100 e to the kt. And we only have one other piece of information. We know the half-life is 1,590 years. So we know that the mass after 1,590 years will be half of the original 100, so 50. So we can go ahead and use that information. So mass after 1590, that's 100 e to the 1590 k equals 50. So we get e to the 1590 k equals 1/2. And it's the half-life, so hopefully that makes sense that that's half. And if we simplify this down, so take the natural log to both sides, simplify everything, we end up getting k to be negative ln of 2 over 1590. And that would be our exact value of k. And this one's not too bad. So we'll go ahead and just leave it exact in this case. So m of t is going to be 100 e to the negative ln of 2 over 1590 times t. This would be our general formula for the mass of the sample that remains after T years. If you're ever on the fence about whether to use the exact number or the approximate number, go with the exact number. Exact numbers are always better, unless the question specifically is having you plug in specific numbers that then you need to round to get an answer within the context. So like for part B, find the mass after 1,000 years. So after 1,000 years, we're looking at mass of 1,000. Now, we know that the half-life is 1590, and this is less than that amount of time, so it should still have more than 50 milligrams left in it, just as a nice kind of mental check here. So we get 100 e to the negative ln of 2 over 1590 times 1,000. And this, if we crunch these numbers in a calculator, we get about 65 milligrams. So our quick mental check was on track. We know it takes 1,590 years to reach 50. So in only 1,000 years, it still has 65 left in it. Now, kind of on the flip side of this question, for part C, when will the mass be reduced to 30 milligrams? So instead of saying, here's how much time, find the remaining mass, they're saying, here's the remaining mass, find out how much time this takes. So we want the mass for an unknown time, so that's 100 e to the negative ln of 2 over 1590 times t. We want that mass to be equal to 30. So we go ahead and divide the 100. So that's 30 over 100, so that's 3/10. Take the natural log, simplify. Oops, forgot the t right there. Take the natural log of both sides, simplify that down. We get t equals negative 1590 times ln of 3/10 over ln of 2, which is approximately 2,762 years. So it takes 1,590 years to reach half, which is 50. In 1,000 years, it's down to 65. And by the time it gets down to 30, it's almost gone through 2 half-lives, right? It would get down to 50 and then down to 25, technically. So almost 2 half-lives. So 2,762 years to get resulting down to 30 milligrams. One common application of this directly proportional relationship between rates of change and size of a population that we can apply to exponential growth and decay is Newton's law of cooling. Newton's law of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings. So here's the formula. So we have dt. So this is a derivative of temperature with respect to time equals k times t minus t sub s. Okay, so again, just to explain what this means. So the rate at which the object cools is directly related to the difference in temperature between the object and its surroundings. So in other words, the bigger the temperature difference, the faster it cools. Okay, so like if you take an object right out of the oven and you put it right into the freezer, the temperature difference between the object and the freezer is a huge difference, and it's going to cool very, very quickly because you put it in the freezer. On the other hand, if you take an object that's been sitting on the counter and you move it into a room that's only a few degrees cooler than the room it was sitting in, it's going to take it a longer time to cool down because it's already really close to that same temperature. Okay, so the greater the difference in temperature, the faster the cooling occurs. So here's some additional information for us to fill in here. Over here is the graph of this situation. So you can see here's the surrounding temperature, whether that be in the oven, in the room temperature, in a fridge or a freezer, whatever the case may be. This is the surrounding temperature, and this is what our function looks like. You can see it does look like an exponential decay graph. So it cools very quickly at first, right? So you've got steep slope, and this distance is pretty great. Whereas by the time you get over here where the distance is pretty close, it levels off and the slopes are not very steep anymore. So Newton's law of cooling satisfies, again, this relationship, this directly proportional relationship, where we call y t minus t sub s. So that's the difference in temperature. So again, this represents the difference in temperature. And y of t, so this function that we can use to solve this problem is y of 0 times e to the kt, with y of 0 being the initial difference in temperature, right? So that's the starting temperature minus the medium that it's sitting in, surrounding temperature. So this is the initial difference in temperature. So let's take a look at using this law in an example. A bottle of soda at room temperature, 72 degrees Fahrenheit, is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the soda has cooled to 61 degrees Fahrenheit. What is the temperature of the soda after another half hour? And then how long does it take for the soda to cool to 50 degrees Fahrenheit? Okay, so a lot of information here for us to take in. So we know the room temperature. It went from room temperature into a refrigerator. So this is going to be our surrounding temp. So T sub S is going to be the 44. We know that the initial temperature that the soda is at is the 72 degrees Fahrenheit. So that's going to be T of 0. And we know that after a half hour, it has cooled to 61 degrees Fahrenheit. So the temperature after 30 minutes is 61 degrees. Okay, so let's set this up here. So we have our proportional relationship. So dt equals K times the temperature minus surrounding temperature, which we said is 44, right? T sub S. If we take it at time 0, so our initial time, that initial difference in temperature, y of 0, so that's T of 0 minus T sub S. It started off as 72 degrees minus the fridge temp is 44. So that's 28. Okay, so our initial temperature difference is 28 degrees Fahrenheit. So our formula, y of t, is going to be 28 e to the kt. And now our job is to figure out what k is. If we can figure out what k is, then we can start actually solving problems with it. So we need to use the other piece of information that we know. We know after 30 minutes, it's cooled to 61 degrees Fahrenheit. So since T of 30 is 61, Y of 30 is the difference in temperature, 61 minus the 44, because the fridge temperature hasn't changed. And that's only 17. So we can use this now in this formula. So we'll have y of 30 is 28 e to the 30k equals 17. If we solve this for k, we get ln of 17 over 28. All over 30, which is approximately negative 0.01663. So our formula for temperature difference becomes 28 e to the negative 0.01663 t. And yes, the K value can be negative, and it should be negative here because we're talking about exponential decay. The amount of temperature is decreasing as time passes. Now, the question didn't ask for the difference in temperature after another half hour. It just asked for the temperature after another half hour. So we need to get the formula for temperature, just in general. So we know that the difference in temperature is just T of T minus T sub S, right? It's the temperature of the object minus the surrounding temperature. We want this one. So we're going to go ahead and add T sub S to both sides of this. So the temperature is going to be Y of T plus T sub S. And we know what both of these are. So Y of T is this formula right here. So temperature of the object is going to be 28 e to the negative 0.01663 T plus surrounding temperature of 44. So the temperature of the soda after another half hour, well, 1/2 hour already passed. That was 30 minutes. Another half hour passing will put the time at 60 minutes. Okay, be very careful to be consistent in your units. If you used 30 here, don't use 1 down here for 1 hour, because then it'll be like you're doing it for 1 minute. If you want to use 1 for 1 hour here, you need to use 1/2 for a half hour up here. But as long as you're consistent with your notation, then you should be fine. So, but T of 60. So it's just going to be 28 e to the negative 0.01663 times 60 plus 44 is approximately 54.3 degrees Fahrenheit. So in the first half hour, the soda cooled from 72 degrees to 61 degrees. So it dropped 11 degrees Fahrenheit. From 30 minutes to 60 minutes, it dropped from 61 to 54.3, so a little less than 7 degrees Fahrenheit. So the rate at which the temperature is dropping is going down, right? It is still getting colder, but not as quickly as it was back when it was a warmer soda. Now, for part B, how long does it take for the soda to cool to 50 degrees Fahrenheit? Well, this is kind of like what we saw in one of the previous questions. You're using the same formula, just kind of looking for the other piece of information. Here we said, here's the time, find the temperature. Now they're saying, here's the temperature, find the time that goes with that temperature. So we're going to have T of T equals 28 e to the negative 0.01663 T plus 44 equals 50. So we go ahead and subtract the 44 over here and then divide by the 28 to everything. So we get e to the negative 0.01663 T equals 6 over 28. So the value of T that we get, if we solve this out, is ln of 6 over 28 all over negative 0.01663, which is approximately 92.6 minutes. So for the first 30 minutes, it dropped about 11 degrees. In the next 30 minutes, it dropped less than 7 degrees. In the next 32 minutes and change, it's only going to drop 4 more degrees, right? It's going to go from 54 degrees roughly after 60 minutes to 50 degrees after another 32 or so minutes. So it is still going at a decreasing rate. But now we can use, again, this general formula to identify both temperatures and times given this situation. And if it was placed into a different medium, we could then calculate based on that surrounding temperature. If it had a different starting temperature, we could calculate all of this similarly. But that is the end of section 3.8. And that concludes our discussion on exponential growth and decay and how they relate to derivatives and calculus.